What's up guys, Mati here. In today's episode we're going to see a lot of new and fascinating concepts, and these are the functional programming patterns. Have you ever heard about the word monad before? I know it sounds scary, but actually you don't have anything to worry about because I'm going to teach you all you need to know in order to use it effectively. So, welcome to Programming with Mati. In our last episode we said that the building blocks of functional programming are types, values, expressions, and functions. Just as we have design patterns for object-oriented programming, we also have design patterns for functional programming. I'm going to explain some of them, but before that, I want to give you a jargon alert because I'm going to use very weird terminology, so stay at your own risk. I'm going to start with one pattern which is very well known in the Java world, but I think it's a good pattern to introduce all of the other ones, and it's the optional pattern, and I'm calling this avoiding the billion-dollar mistake. In 1965, Sir Tony Hoare introduced the concept of null pointer to the Algol family of languages, and Java is a grandchildren of this language. He called it his billion-dollar mistake, and I think we Java programmers know what he means by that. We encounter null pointer exceptions everywhere, and we always need to guard ourselves from referencing a null. Every Java developer has to add an if condition saying if this is not null then do this, and if this is not null do that. Quite annoying. And then even if you guard yourself of most of the nulls, sometimes you forget about one and then you end up with a null pointer exception. Because in Java we can reference null, all our programs are filled with guard statements saying if this is not null then do this. And optional is a concept borrowed from functional programming, and it represents the possibility of a value not being present. So mathematical functions always need to be defined for all possible inputs, right? So if you see these two functions here, it's a divide function, a very simple function. It receives two doubles and it returns the division between them. But what happens? If y is 0, then we get an exception. And why do we get an exception? Because we cannot divide by 0. So this signature right here is lying to us. It says it can receive any double, and it will always give us a double, but actually it won't. There are some cases in which it won't return a double, it will throw an exception. So in functional programming it's important to define a function for all its inputs. So we could, for example, restrict our input, saying, for example, that you cannot put 0. We could define a new double without 0 type and send here that type. So we basically restricted the input, or we can accommodate the output, extending the output by adding optional. So basically what we do here, if y is not 0, then do the division, else return an empty optional. And we've seen optionals in our tutorial before, but in here what we're doing is basically we're wrapping our values into an optional type. So in the case that there is a value, this optional type will have a value and the isPresent method will return true. And in this case, because the optional is empty, when we call isPresent, it will return false. And we can see how we use it here. So this is an implementation of some function without optional, and the param may be null. So we check if the param is not null, and then we do return, and else we return the default value. Now, if we receive an optional, we actually cannot forget to check for the null like we could here, because the value tells us that this is an optional, and we need to basically reference the optional first, and then we can do the creation of the new object, and else we return the default value. So it's helpful, but I don't see a real advantage here. It's not a huge advantage, let's say. It gives some clarity about what the possible inputs are and so on, but still it's not a huge advantage over what we have in Java. But we will see how this becomes a more powerful thing when we add the next patterns. So one of the first things that we would like to do with our value is actually operate with it, because we have an optional now and we don't know how to operate with optionals. I cannot apply the string functions to an optional string. I need the actual string to operate with it. So how can I do that? Of course I can unwrap it, as we did in our code with the get method. But that's usually very inconvenient, because if I have an optional and then I unwrap it, and then I need to deal with the case if the optional wasn't there, so I end up having having to check if it is null or if it is present. So how can I operate with the optional as if it were an actual string? What I'm asking here is basically this. So functions are mappings between types, right? For example, we have the integer function to string, and this transforms an integer into a string. We also have the double value of function, which turns a string into a double. And these mappings are basically functions between different types. And this is what it's called the category of types. So basically all the types in our language. And so when we create an optional, we're actually moving into a different category. It's a different kind of category, and it's a optionals types. And in these optionals types, we don't have, or at least we don't know how to operate between them and keep our original transformations, our original mappings. So how can we do that? And this is where the map function comes to the rescue. So what we end up having here is a pattern called a functor. Optional is a functor because it has a function map which preserves this structure that we have here. With the map function, we can basically operate optionals as if they were regular objects, regular types. So if we have an optional integer, we can do map and transform it into a string using the toString method. Also, if we have an optional string, we can do map and double value of to turn it into a double. And we can also compose toString and value of, and then wrap it into map, and it will go directly from integer to double. This is what a functor is. It transforms the category into the optional category, but still we get all the different mappings that we had before. All the different functions that we had between these objects, we still have them thanks to the map function. So this is a very cool pattern. So yeah, basically a functor is a transformation that maps objects from a category into objects of a different category, preserving structure, meaning all those mappings between the objects. So the objects in our categories are the types, the mappings are the functions, and we preserve that structure with the map function. So the map function becomes our savior in preserving structure, and we have a new category with embellished functions. So there is a special kind of functor called an end of functor, which transforms things of a category into things of the same category. In programming, we are only using one category, which is the category of types. Like if we see this in our previous diagram, even though we created a new category, this is still inside the category of types, because optional types are still types. So technically, our optional is also an end of functor. So and here how we can see how optional is a functor. So here we can see how we can operate with the parameter being an optional. Even though it is an optional, I can use map and send the constructor function as a parameter here. This is a special function that optional have, where if the value is not present, it will return this value that is here, the default value, or else it will return the actual value transformed by the map function. So this is a very, very useful and a very expressive way to deal with optional values. You can see here we have to do an if statement and check if it is not null, in here, we just assume with the map function that the value is present, and we can chain map operations here. And in the end, if the value is not present, then we handle it differently. So it's a bit more expressive and easier for us to use. So in our last episode, we created a tutorial and we used the functor pattern there. So for example, if you go to the distance method in the class path, you will see that we have the list of segments, and what we want to do is actually operate on the distance. But since we have a list, we have to be able to access the distance that is in the list. So with the map method, what we end up doing is we create a new stream of all the distances basically. So if you see here, we have a stream of segments, and then after this, we get a stream of big decimal. Every value in our stream is transformed from segment to big decimal. If we only have one segment, we can, so let's say we have one segment here. If I do new segment, I can always say distance, right? But since we have a lot of segments, how can we get the distance of all of them? Basically, with the map function, we can do that. And we end up with a stream big decimal. So you see how the functor pattern is applied. Now that we have the stream big decimal, we basically can operate as if they were big decimals instead of segments. That is a cool feature of the functor pattern. In traditional imperative programming, what we would need to do is basically do a for loop, and for each segment get the distance and put it into a different list or stream. But with this approach, it's way easier. So now we're going to move on to the next pattern, which is called a monoid. Imagine that we have a binary operation. For example, the addition between two integers. Addition of integers has a few properties that allow us to calculate the addition between more than two integers, because a binary operation is basically an operation between two operands, so two parameters. And if we want to extend it for more than two, then you have to have certain properties. And for this case, what we would like is to have a property called associativity, which is if we have three integers, a, b, and c, we could do a plus b, and then we can do plus c, or we could do a plus b plus c, and we'll get the same value as a result. So basically a monoid is something that allows us to apply a binary operation, a function that is supposed to be applied for two operands to more than two operands. So if we have a list, for example, and we want to feed it a binary operation, we want to apply to this list a binary operation, we can apply it, and because of the loss of associativity, we can be sure that even if the algorithm applies from the beginning and from the end, we will get the same result. And then we also have another property, which is the neutral element or the identity element. In the case of addition of integers, the neutral element is 0. And if we add elements to 0, we get the elements. As we can see, the identity element allows us to handle the cases in which we don't have elements. The binary operation is complete and we get the monoid. A monoid is basically the set of elements, the associative binary operation, and the identity element. They all form a group, and this group is called a monoid. In everyday terms, a monoid allows us to extend a binary operation to more than two values. So an example of a monoid is something that we have used in our tutorials, and it's called the reduce function of the stream interface. And we can see it here. We do stream, then we map it to distances, and finally we use the reduce operation on the resulting stream. And the reduce operation applies a binary operation. So now that we know monoids, we can put it together with functor, and we can see the pattern called map reduce. So the pattern map reduce is usually used to convert non-monoids into monoids. For example, Our segments are not monoids. They don't have, we cannot add segments together and so on. But we can map them into something that can be added, and then we can reduce them. And that is why this pattern is called map reduce, because we have something that is not a monoid, because the elements are not, they don't have any associative operation whatsoever. So we turn them into elements of a monoid, and we basically operate as if they, now with the actual monoid, we can reduce them and so on. And this is what we did in our tutorial. So basically we used the functor pattern, we used the monoid pattern, and we combined them together to get the map reduce pattern. And this map reduce operation is very useful in data analytics. So, and now I guess one of the most complex things that we are going to see today is this pattern called the monad. I've seen a lot of different tutorials in internet about monads, and I've noticed that there are some good ones and there are some that are not that good, and people are usually scared of this term, but there's no reason to be scared because we used monads in our tutorial and they're very easy to understand or use. Sometimes the math behind a monad can be complex, but it's not really that hard to use. We are going to talk what it is and how we can use it. So we use the monad pattern to add effects to our functions in a controlled way. We functional programmers like to deal with pure functions, okay? But there are a lot of things in our programs that are not pure functions. Because, for example, if we have a console application and we input text from the command line and we use a console.getChar, for example, to get the input, that getChar function will always return different values and it doesn't take any parameters. So it's not a pure function because for the same input, it always returns a different value, and that makes it not a function. So monads are used to contain those effects. So basically we deal with those effects by taking our pure functions from the types category into the monad category. So a monad is actually a functor that takes our functions, our pure functions, from the category of types and pure functions to the category of monads and side effects. And it's a very explicit way to deal with side effects. Because monad have side effects, we basically need to compose those side effects. Usually a monad has a unit function to create a monad of no computation value, and then it has a function that allows us to compose monads together. This function is often called bind or flat map. So Java has three inbuilt monads, which are stream, optional, and completable future. A stream is used to process elements of a collection in a pipeline of transformations. So, and it's a monad because it has a flat map method that allows us to compose multiple streams into a single stream. So, if you have a function that returns a stream, you can flatten it basically into a single stream. So let's say you have a stream, right? You map each element of that stream into a stream as well. You will end up with a stream of streams. But sometimes what we want is actually flatten that so that we have a single stream. So what we do is basically use flat map, and in that case we will end up with a single stream, which is the concatenation of all the substreams. And then we have optional, which we already saw, and this one represents the possibility of the value being missing. If we have multiple optionals, what we can do is use flat map to combine them together into a single optional. If we have a value, for example, an optional value, and then we want to operate on it, and that operation returns in itself another optional, we need a way to flatten it into a single one, because we would end up with an optional of integer, for example. and we don't want that. So we want to keep it into a single optional. So with the flat map operation, we combine them. And the same happens with complete of the future, which represents tasks that will be executed in the future. So this can be composed with a method called then compose, but which is actually flat map as well. And here is an example of monad compositions with optional. So without optional, let's say we have a method here, get r, and this can return null. And then we have some function which takes p and returns t. So we need to check if p is not null, then we can go and get r with p. Then if r is not null, we can create a new t with r. Else we will return the default value. This is what we would need to do. And here with the optional monad, what we can do is basically use the flat map method to combine the side effects of the values not being present. So basically we get an optional param p. This method here now returns an optional. So what we do is we get r. So this returns an optional of r, and it's not an optional of r like map would do. We have a map operation here to use the constructor, and finally we do or else return the default value. And as you can see, we didn't have to check twice for null because the side effect was joined. The monad has joined the effect of the value not being null. If the value is null here, it will go here directly. If the value is null here, then it will go here as well. So we have joined together the side effect of the value not being present. And this is the power of the monads, that they can combine functions and side effects. And that's why functional programmers like them so much. And there is a lot of different monads that you will see around, like the try monad for handling exceptions, the IO monad to handling input and outputs, the continuation monad, the future monad, or the promise monad also called in JavaScript. So these are all monads. And this is very, very useful because it allows us to compose pure functions with side effects. You can also tell me which of these blocks of code are more expressive and more clear for you. In my opinion, this is clearer. It's shorter and it's very concise, and I don't have to do any if statement. I just need to operate. So you tell me in the comments if you think this is very helpful or not, but I think it is. As we said, monads are used to add effects to our functions, and we have seen that monads are actually functors. And not only they are functors, but the flat map operation combines monads together. So the flat map, it's a binary operation between monads. And we also have a unit operation to create monads and compose them. So does it sound like a monoid to you? Well, that's because it is a monoid. So the full definition of a monad is that a monad is a monoid in the category of endefunctors. And that is when everything becomes full circle. Yeah, I know. It's a lot to grasp, but let that sink in, and let me know what you think about all this in the comment section. Alright guys, that was all for today. So what did you think about these patterns? I honestly find them very fascinating, but I want to hear from you, so let me know what you think in the comment section. In the next episodes, we're going to learn how to implement one of these monads, and we are also going to go a little bit more in depth with some of the particularities of the different monads that we have in Java 8. So I'll be waiting for all of you, and before you go, remember to smash the like button, comment and subscribe. See you!